to pronounce by no means. So fortunately, I have two names. So also call me Rudi if it's easier. Also for any potential questions. So this holds for the audience as well.
Great, fantastic.
You can see my slides, right?
Yes, I can see your screen, which is great. So we'll start soon. We'll also record the meeting, but before we start, maybe just one more question. Would you like to make this lecture more interactive so that the participants could interrupt and ask you questions? Okay, so we can try to do it because we'll also have a Q&A session at the end.
All right, but so I read on mine. I think it's in everyone's interest if unclear parts are clarified as we go. So I'm happy to take questions on the fly.
Okay, perfect. So I will start with just a brief introduction. So I will now share my screen.
All right.
Okay. Can you see my slides now?
Yep.
Perfect. All right. It seems that we started recording the meeting, so I think we can start. So hello, everyone. Welcome to the next quantum computing meetup organized by a group from Washington, Warsaw, and Toronto. My name is Pawel. I'll be the moderator of this meetup, and today we have a pleasure to host our great speaker, Jernej Rudi Finžgar, and he will tell us about new approaches to near-term quantum optimization. Before we start, just a few announcements. This meeting is recorded, so hopefully the video will be available on our YouTube channel, and there is also a live streaming. If you have any questions, feel free to raise your hand or post your question on the chat. And if there are some urgent questions, we'll try to interrupt. And there will be also a Q&A session at the end. We would also like to announce some of our next meetups. So the next Washington Quantum Computing meetup will be in December. The speaker is Tim Linke. He will tell about gaming for quantum literacy. And then the next meetup will be in January, and Dr. Anup Krishnan will tell about accelerating materials discovery with AI and machine learning. Then at UNIS in March, we'll tell about compiling resource-efficient programs with numerical instantiation. And finally, in May, Dr. Bruna Araujo will tell about moving towards compactification of the many body wave function using a bottom-up approach. We would also like to thank our partners and sponsors for supporting us, and of course, thanks to Helen for organizing everything. And with this, I'll stop sharing my slides. And Jernej, if you are ready, you can start sharing your slides, and we can proceed.
All right. Can you see my screen?
Yes, I can see your screen.
Awesome. Let me just see if my pointer options are enabled. They are. Great. Thank you, Pawel. Thank you, Helen, for the introduction and invitation. It's a great pleasure for me to give this talk here in this audience. So as Pawel said, I'm happy to take questions on the fly. So please feel free to interrupt me. Let's make this as informal and as interactive as possible to the benefit of everyone. So to introduce myself, I am a PhD student at the Technical University of Munich, but I'm also affiliated with the BMW Group. So I'm kind of, let's say, what we call in Germany an industrial PhD candidate. And my topic or my focus field is quantum optimization algorithms. So let's dive right into it. What is combinatorial optimization, and why do we ultimately care about it? So mathematically, combinatorial optimization, is trivial to state. It amounts to minimizing or maximizing, depending on how pessimistic or optimistic your outlook on the world is, a cost function over a collection of discrete, for example, binary variables. With this, I mean you have some variables x, which can, for example, take the value 0 and 1, so they're binary. And then you're trying to find the minimum of, some cost function, which is, some expression involving these variables x. And although it's, very simple to state, this is actually, first of all, super useful. So you can model a, vast variety of tasks and processes across, both science as well as industry, including, for example, of course, at BMW. And as such, this has far-reaching implications. However, the problem is that oftentimes, or actually for most of the interesting cases, finding the optimal solution of such a problem comes at great, that is exponential in n, where n is a number of variables, cost in terms of the runtime that is required to have optimality guarantees. And as is kind of, I would say, a tradition, I would say that quantum computing has been applied to this realm sort of as, to address this computational bottleneck that arises with this exponential in n cost that comes from solving when you try to solve these types of problems. And as I mentioned, I just give here one very simple example of, or one very interesting example that of an optimization problem that arises along BMW's value chain. So here we have, a schematic illustration of the problem that we call robot motion planning. So imagine you have a robot which has to, perform some task along a graph that, kind of is defined like this. Now the question is, what is the optimal way for the robot to perform such a task? So to, kind of traverse these nodes and these edges. And you can imagine, there's multiple such robots and they cannot collide and so on. So there's, a whole lots of complexity that one can build on top of this, like very similar or very simple looking example. And as it so happens, it's actually, something that BMW actually faces in their production line when the underbody of the car has to be sealed. And I brought a small visual demo of this. So this is actually a video taken in a BMW production plant, and you can see one such robot applying PVC, that is a sealant to kind of seal the gaps between the different parts of a car underbody. And there's actually prior work from some of my colleagues and actually some collaborators from Amazon that were kind of exploring quantum and classical methods for the solution of such a problem. And I give the reference here for anyone who's interested. Yeah, so I mentioned that quantum computing is used to address this computational bottleneck. And in this NISQ, noisy intermediate scale quantum era, mostly two types of approaches have been at the forefront of these endeavors. So I classify them here as in two kinds. First, you have analog approaches and digital approaches. In analog approaches, or these are mostly known under the umbrella term of quantum annealing, or alternatively adiabatic quantum computing, which is based on top of seminal works from Kadowaki and Farhi at the turn of the millennium. And what these amount to is basically some sort of a continuous deformation of some simple Hamiltonian, of which we know how to prepare the ground state, and then we deform that Hamiltonian continuously to the target Hamiltonian, which encodes the optimization problem that we're interested in. For example, the robot motion planning that I showed you before. And in recent years, D-Wave has been, I would say, probably the biggest proponent of quantum annealing in these analog approaches. However, in last couple of years, also neutral atom quantum computers, such as the ones developed by QERA or Pascal, have gained some traction in this realm. Over in digital approaches, I think the most famous example of a NISQ algorithm is the so-called quantum approximate optimization algorithm, or QAOA, developed by Farhi and collaborators in 2014. The main idea there is to set up a variational circuit which consists of a layered-wise application of parameterized unitary. And these parameters are then optimized in a variational fashion with a classical optimizer, such that the energy of the quantum state with respect to the target Hamiltonian, which includes the optimization problem, is minimized. And with that, we kind of hope that we combine the powers of quantum and classical computers to arrive at good solutions to the optimization problem. And this has sprung up a kind of a vast variety of alternatives or derivatives kind of from QAOA, both in terms of parameter initialization or enforcing constraints, or using this in a recursive manner, just to name a few. So to go back to the agenda of my talk today, I actually during my PhD so far, I've delved a bit into both of these fields of near-term optimization, both on the analog side, which is what I'll be focusing on first, with this topic of designing quantum annealing schedules using Bayesian optimization, where I will do a brief overview of what Bayesian optimization is, which I think is a topic that many of you might find handy in fields which are also far removed away from anything to do with quantum technology. So I hope this brings some value also to such an audience. And then I want to showcase my approach on some of the on the exciting new Gora device. Then in the next part of the talk, I will turn my attention to the more gate-based or digital approach, which is kind of building on top of QAOA, and where we propose this quantum-informed recursive optimization family of algorithms before concluding. So yeah, let's go first into the analog part of the talk. So I'm sure that at least some of you in the audience will have seen this very impressive paper from that was published in Science, I think, in 2022. I think it's safe to say this was probably my favorite paper of 2022. And the whole idea is to use a neutral atom quantum computer to encode and solve maximum independent set problems. So maximum independent set problem, I'll talk a bit about that later, but for now, let's just think of that as some optimization problem that has potentially practical relevance. And the way this was done in this very nice paper was that a analog protocol was set up and then classically optimized such that basically better and better solutions to the optimization problems were obtained. And I was very excited to see that when Gora, which is a spin-off from some of the research groups that were behind this paper, put their quantum computer as publicly available through Amazon or AWS's Bracket service. I was very excited to try it out and see if I can see similar results and potentially build on top of that. So when I read the fine print of the paper, I realized that, well, roughly 100,000 calls to the quantum computer are required to optimize or to obtain results for a single graph instance. And I thought to myself, all right, sure, why not? However, up until recently, I was only able to obtain like 10,000 shots per week through Amazon Bracket. I think since then, the availability of the device has increased. So I think that now probably more like roughly around 40K per week are possible, but it's just my estimate. In any case, this is far below the 100,000 required just for a single graph instance, right? And as a PhD student, I want to get some results in. So I asked myself, how do I optimize the adiabatic protocol more efficiently, right? So what do I do to require that we'll still optimize the protocol such that it will produce good results, but at the same time make it feasible for implementation through Bracket. And that kind of naturally led me to Bayesian optimization. And I summarize my approach, or our approach, in this figure. So the way we set out to do this task was to use Bayesian optimization, which is an efficient way of optimizing black box functions, to optimize analog protocols for a QERA device, which was then evaluated on the hardware, and then this kind of result, or this evaluation, then informs the Bayesian optimizer to produce the next kind of set of schedules, and this kind of proceeds in an iterative fashion until convergence, or until the resources were exhausted. So what is Bayesian optimization? Bayesian optimization is a tool which is designed specifically for optimization when evaluating the objective function is expensive. Expensive in this case can mean either in terms of monetary cost, or in terms of the duration, or for example in our case just the sheer lack of availability. So this has found great success, for example, in machine learning, where you do, for example, hyperparameter optimization that requires training a whole model to evaluate just a set of hyperparameters. So this is obviously very expensive, and we would like to avoid doing this too often. So we use an efficient way of optimizing this. So Bayesian optimization, let's say, let's do a brief tutorial or a brief intro to BayesOpt. Let's say we have a objective function f of theta that we wish to maximize. So theta here are some parameters that we're interested in, and f is sort of like our figure of merit. We can think of this as, for example, the quality of the solutions obtained from a quantum computer, for example. And let's say that we observe f, meaning that we have access to the value of f at a certain set of parameters, right? So that, for example, we are able to evaluate a couple of protocols on a neutral atom quantum computer, and we get some energies out. Now the question is, how do we find the maximum of this figure of merit, or the minimum equivalently, using as few evaluations of this function as possible? The way this is done in Bayesian optimization is that a model is built of the objective function. So basically, you try to incorporate all of the knowledge that you have from prior observations of the cost function to build a model f tilde of theta, which is constructed from Gaussian processes, which is some, I would say, well-studied and well-understood tool from probability theory. And the essence is that you build this, you assume that your cost function is some sort of a probability distribution over the functions in this, interval of interest. And you have also, of course, some uncertainty, right? So you're not exactly sure where the model that you see here lies, but you assume it lies somewhere within this interval. And then you kind of adjust the model as the observations come in, and you see that the shape of this model kind of starts slowly adapting to the actual shape of the figure of merit curve. Now, the crucial step of Bayesian optimization is that how, once you build this model, you also use it to predict or kind of suggest the next point that should be evaluated. In this case, you combine the properties of this model into some heuristic, which you call the acquisition function, and this acquisition function basically tells you this is probably the best point to sample next, and it compiles this information based on two factors typically. The one is what is the expected value of the function in this particular point, and the other one being how much do I know about the values of the function in this particular region. And you can see that, for example, here now we have, we knew of these 2 points, and then we suggested this one. And you see that, once we added or evaluated another point, that the model of the function kind of adapts to the actual curve, or starts adapting. And then now it suggested this point, probably because, we didn't know much about the value of the merit function in this part of the interval. And now we adjust, and again it suggests this point, which as you can see is already pretty close to the maximum. So of course this is a cherry-picked example, but it I think gives a nice, let's say, intuition as to why and how Bayesian optimization is able to find good parameters for quantum annealing protocols efficiently. Exactly. So another nice caveat or another benefit of Bayesian optimization is that, first of all, it's gradient free, meaning that there's no problem of computing gradients via parameter shift rules or something like that. There's no requirements or very little requirements on the hardware. And the second thing is that it's able to handle noise, meaning that since everything is done in this Bayesian framework, even if these observations are slightly noisy, this can be nicely incorporated into the pipeline. All right. So just to kind of give a refresher, maybe this is a nice opportunity for questions. The whole pipeline then looks as follows. So you parameterize, you specify a set of parameters which parameterize a certain schedule function, which you then evaluate on a quantum hardware. So basically, this is some sort of annealing protocol which has to take some parameters, which is then evaluated on quantum hardware, and then kind of which in turn provides the information of the figure of merit, and then a new set of parameters is specified, a new parameter schedule, and so on. And then this kind of proceeds until we've reached the desired quality of a solution. Right. Any questions up until this point, or is everything more or less clear?
Okay, let's see. I don't see any questions on the chat, but maybe someone would like to unmute and ask. Please raise your hand if there are any questions. I don't see questions, so I think we can continue, and maybe there will be some questions at the end or later.
So yes, one of the applications that I alluded to in the motivation slide of this talk was solving the so-called maximum independent set problem. And I would like to take a couple of minutes to introduce the problem and also explain how it is mapped to a neutral atom quantum processor, because I think it's a very fascinating example of how one can leverage the underlying physics to encode an optimization problem very natively in quantum hardware. So the maximum independent set problem amounts to finding the largest subset of vertices in a graph that is not connected by an edge. So you see an example maximum independent set here, indicated by the red nodes, and you see that no 2 red nodes are connected by an edge, and this is the so-called independence constraint, because each 2 nodes are independent in the sense that they're not connected by an edge. And it's actually NP hard, meaning that it's exponentially difficult for a general graph to find such a configuration of vertices, meaning that it is a interesting problem from the perspective of combinatorial optimization. On the other hand, I would like to mention that it's also practically relevant in areas such as network design, etc. So it's both difficult and interesting, making it a very nice problem to study. There is a specific family of graphs which is particularly amenable to being mapped to neutral atom quantum computers. and these are called unit disk graphs. They're called unit disk graphs because they are formed by just positioning a collection of vertices on the plane, and then only connecting vertices which are within a certain distance of each other. So, for example, take this blue vertex here. You'll notice that only vertices which are closer than some distance to that to this particular center node are connected by an edge to this particular node, right? And this is important because this maps to a natural or a very natural physical property of neutral atom quantum computers called the Rydberg blockade. So in a Rydberg blockade mechanism, what happens is you have atoms trapped in an optical lattice, like the one you see here. So, for example, imagine all of these atoms, or all of these circles correspond to atoms, which you can arbitrarily position using optical tweezers in a almost arbitrary configuration. And then basically you shoot lasers at these atoms, and with that you can excite them in the so-called Rydberg state. A Rydberg state is a state of the atom in a very highly excited orbital, and as such, it kind of attains this so-called huge blockade radius, in which no two atoms can be simultaneously excited. Meaning that if you have a Rydberg atom, meaning a highly excited atom, none of the very neighboring, close by atoms will also be able to simultaneously be excited. And this, if you think about it, is exactly the constraint that you have in the maximum independent set problem. So basically, if one is able to position atoms on a 2D in this 2D configuration by preparing the ground state of the Rydberg Hamiltonian, which governs the dynamics of such systems, one effectively solves the maximum independent set problem. And I think that's a very very cool mapping. And what I like particularly about this is that it's super close to the hardware, right? It's literally the physical principles underlying the dynamics that actually enforce the constraint of the optimization problem. And yeah, you can prepare, without going into details too much, you can prepare the ground state of such a Hamiltonian, for example, using the adiabatic protocol, which looks like this. So basically, this is the Hamiltonian. Not going to go into the details too much, but basically, you optimize two parameters of this Hamiltonian, or let's say you parameterize them, and then you optimize the parameters such that you prepare the ground state of this Hamiltonian, which encodes the maximum independent set problem, as discussed before. And in the paper that I showed in the motivation, they did this with some optimizers. In our case, we used Bayesian optimization, and we were able to do this using 20 times less interactions or shots from the device than in the original paper, meaning that we could get 20 times more experiments done, even with the limited availability. First, we tried designing schedules in classical numerical simulations of this Hamiltonian, and then test the obtained parameters on QERA hardware. We did this for, obviously, of course, for only very small systems, because these are accessible in numerical simulations. So this is kind of the naive. These are results from the naive protocol that one would do without optimization, and then there are two different flavors of Bayesian optimized results. And you see that one can very clearly tell the features of the maximum independent set on these graphs, while here it seems very murky, or you would be hard pressed to tell me which of the colors are indicating that a certain vertex is in the independent set or not. What was likewise very nice to see was the comparison between results in numerical simulations and then on actual quantum hardware. So here I plot the probability of finding the maximum independent set for a family of such graphs. And the lighter shades, so the lighter blue and the lighter red, indicate results from numerical simulations. whereas the darker shades are from results obtained from the actual, neutral atom quantum hardware. And we see that there's a very nice agreement between the kind of theoretical and experimental results, which hints that there's actually very low error rates on the device. Of course, we didn't stop there.
Rudi,
device.
Yeah. May I interrupt? Because there was one question regarding the previous slide. Yes, this one. There's a question from a student. What do these DR and cost indexes mean next to H, which is
yes.
the Hamiltonian?
So I glanced over this in the interest of time, but I'm happy to explain, of course. So this is the two parts of the Hamiltonian, which one has experimental control of in a Rydberg atom or a neutral atom quantum computer. The DR stands for driver. So this is the so-called driver Hamiltonian. Driver in the sense that, it has these Pauli X terms, which, flip bits from 0 to 1 or, 1 to 0. So basically, this kind of is performed by the so-called Rabi oscillations between the Rydberg excited state and the ground state. And this sort of, allows us to explore the different configurations, so to say. The cost Hamiltonian is what I described before. So this basically describes this Rydberg interaction, basically that no two nearby vertices or atoms can be excited at the same time. And this delta term favors that as many as possible atoms are excited, meaning, we're trying to excite as many of these while not exciting two of them simultaneously, which is exactly the condition that we have in a maximum independence set problem, right? So you're trying to maximize something while obeying this so-called independence constraint. And this is captured by these two terms here.
Okay. Perfect. We have two more questions. Should we ask now? Okay. So one is also rather general. So it's a question that was asked on YouTube, actually. So how does the conditioning of probability distribution works?
It's a very nice question. So basically, you work in this framework of Gaussian processes where you assume that these points, the points kind of that form this purple or teal line are Gaussian random variables. And then you have some correlation between them, right? If 2 points are close together, they're probably more correlated. And this kind of gives you this nice smooth structure. And the nice thing about Gaussian multivariate Gaussian distributions, which is exactly what this is that they are closed under conditioning. And the second thing is they can be specified basically by two parameters, which is the mean function and the covariance function. So basically, all you need to do is change or update the covariance function and the mean function by setting or fixing the value at particular points. And this in the end amounts to basically, some sort of matrix algebra. So there's no need for sampling, no need for any of the advanced let's say statistical tricks. And this is, I would say, also the reason why Gaussian processes are typically used as the model function for or let's say the modeling tool for the figure of merit. I hope that answered the question.
Yeah, I think it was quite good explanation. There's one more question, so maybe I will ask and then we'll move forward. So it's a question from Cayetano. In the real manufacturing processes, there are spatial, temporal, and associated cost variables which are path dependent. Then how can you define the optimization function with path dependent variables?
I mean, this is, I'm not sure I entirely understand the question.
Okay. Cayetano, maybe you can also unmute yourself and clarify if it's fine for you.
Can you hear me?
Yes, yes.
Yeah, I was wondering, because when you show that video from BMW, the manufacturing process, I was thinking that during the process of manufacturing, there are many processes which may be done in parallel. Some are sequential, some are in parallel. So there are the machine tools, they are traveling. There are kinematics of machine tools, which are what I call spatial variables. And at the same time, each process is time dependent, but also when you're trying to optimize the costs, there are different processes, different paths, different way of going with this manufacturing process in terms of what is sequential and what is parallel. So I wonder when you talk about optimization, how you define this function to optimize to reduce your cost.
So I would say in this case, probably the easiest way to think about it is that you have a robot, and this robot is somewhere on the assembly line. So a car comes, and then the robot has to perform some task, and this task is nothing but a sequence of instruction to the robot, right? So the robot has to do this, that, move around, right? And all of these movements, they take some time, and this is ultimately what you're optimizing for, right? You would like the robot to be able to do this as specifically as possible. So maybe I think just like if you focus on this specific task that I was presenting here, I think you can get around maybe you were trying to think of in a too general sense, right? So this is a very like I would say very simple example. Is that clear or?
Yeah, it's okay. Thanks. Can proceed. Thank you.
All right.
Okay, thank you, Rudi, for answering questions. I think we can go on.
Exactly. So bottom line is we have an efficient way of optimizing protocols for neutral atom quantum computer, and yeah, exactly. So and this works well both in theory and in experiment. And finally, I would like to also show some results on graphs which go beyond what is classically simulatable, at least in a very naive way of simulation. So here, we use this to find maximum independent sets on graphs with 137 nodes, which you can actually implement on the QERA hardware. And we optimize the protocols using Bayesian optimization, and then kind of compared the energies of the obtained bit strings or the obtained solutions, as they come from a linear non-optimized protocol or our optimized protocol. And you see that there is a substantial improvement in the performance, to the extent that there's almost no overlap between the distributions of the strings that come from these two different protocols. And again, this is super nice to see, and I would like to emphasize that this has really been done in terms of in a real time or an actual online fashion, where the optimizer was actually sending protocols to the quantum device using the Amazon Braket service, and then obtaining the results to inform the next set of parameters, and kind of proceed in this iterative fashion. So it's actual. So these are actual results from quantum computers. Exactly. Right. So yeah, the take-home message for this part of the talk is that I think Bayesian optimization is a very promising tool for near-term quantum optimization, as it's resource efficient. I think any of you who have tried to access quantum devices will know that this is not straightforward, at least in the NISQ era. And the other thing is that I think there's kind of seems to be some indication recently in the literature that analog quantum protocols seem to require fewer parameters than corresponding QAOA circuits, especially, and this makes them easier to optimize. And this is especially true, I think, for applications where you can really naturally embed embed the optimization problem on the hardware with little overhead. I would like to, of course, advertise our paper, which is available on the archive. Therein, you'll also find results on some canonical toy models with classical simulations of the P-spin model and so on. So if you're interested, feel free to get in touch or check out the paper. I, however, will continue. For those of you who haven't, who are not bored yet, I'll try to bore you in the next 20 minutes when I talk about quantum-informed recursive optimization algorithms. So this is a recent preprint from myself and some collaborators, and the idea is that QAOA, as I've described it before, right? So there's this alternating application of unitaries that are parameterized, and that we then optimize these parameters. That this ansatz is inherently limited because it's local. When I say local, I mean local because it without going into too many details, you can think of it that all of the gates that are happening in here are directly related to or given by the interaction graph of the optimization problem. When I say interaction graph, I mean basically just which variable interacts with which variable in the optimization problem. So which of the two variables are coupled in a sense. And as I mentioned, locality was used in the last couple of years as a key ingredient for several limitation results. This means that the performance of QAOA was shown to be limited when for certain classes of problems due to the fact that the ansatz is local. And this is a lot of hardcore theory, which I think is not the point of my talk today. So I'll focus mostly on how to circumvent or mitigate this problem of locality. And I think this is very nicely illustrated in this example. So this is taken or motivated by an algorithm called recursive QAOA or RQAOA, which was proposed by Bravi et al. A couple of years ago. And the core idea of RQAOA is to use QAOA to measure correlations between variables in an optimization problem, and then use these correlations to simplify the problem. Meaning, you measure the correlations between two variables, and then if they are highly correlated, there is a good indication that the quantum algorithm thinks that these two variables, maybe are, pointing in the same direction, right? In the, let's say that both of them are 1, for example, in the binary case. And in that case, you can replace the value of one variable in the optimization problem with the other, and just remove one of the variables from the optimization problem. And as such, you kind of simplify the problem because it has one variable less. And just to see how this is quote unquote non-local, you can consider this example. So you have variables 1 to 20, with some of them missing in this particular configuration, or let's say this particular interaction graph. So here every edge corresponds to that the fact that these two variables are coupled. And let's say that we've chosen, or that quantum QAOA told us that variables 4 and 8 are correlated. And then we effectively freeze this correlation. We say, well, the value of variable number 4 is just the same as the value of the variable number 8. We can then remove the variable number 8, but in turn, we obtain these new connections between previously unconnected variables, right? So you see that the variable 5 is now connected to variable number 4, and variable 12 is now connected to variable number 4. And as such, this is, a non-local effect in the sense that there is a new connection that breaks with the original connectivity. And this has actually been shown to, in RQAOA, has been shown to lead to, dramatic performance improvements, even or already with, very low depth QAOA, right? So when I say depth, I mean kind of the number of applications of this layered unitary that one does. And typically, what one expects is, the more applications one does, the better the result will be. But of course, this is then also more demanding on the quantum hardware. And going back to RQAOA and the impressive results already with p = 1, so the lowest depth, the question that we asked ourselves was, can we do better than that? Or how to build or how to do even better than that, given that already this very simple rule produced such good results. To this end, we proposed a new family of NISQ optimization algorithms that kind of generalize RQAOA. And the general idea is, I would say, quite straightforward. So you have some quantum resources, be it a digital quantum circuit or some analog protocol, which prepares a candidate quantum state to your optimization problem, and you use the state to measure correlations of polarities of variables that are represented by the Z operators. So basically, you're trying to gain information about the relative orientation of certain variables, and then use this information in classical update rules that simplify the problem. And I will illustrate this for the example of the maximum independence set problem in a bit, but just like to stay on this high level for a second. The idea is to, first of all, as I mentioned, counteract this locality problem of QAOA, and as such, escape this limitation results that are relying on the locality. And on the other hand, also, use the update rules sort of as in a sense of, there's so much research that has been done in classical optimization that it would be a shame not to use all of the techniques that were developed there. And this kind of attempts to bring the best of both worlds together, where the update rules are also informed, or they are informed by quantum resources, but on the other hand, are also inspired by techniques from classical optimization, which might, for example, be good at part of the optimization problem in which quantum resources struggle, and conversely, the quantum resources help the classical update rules in parts that are difficult for the classical updates. And this, kind of is in the hopes of boosting the performance. One very nice, let's say, caveat that one can, or one benefit of this approach is also that one can use these update rules to enforce constraints, which is oftentimes, for those of you who have done some quantum optimization in the past, you'll know that this is oftentimes the pain point of quantum optimization. Let me give you a quick example on the maximum independent set problem. So again, the maximum independent set problem, right? We're trying to find the collection of nodes such that there's as many of them as possible, and that none of them are connected by an edge. And we have these these 4 update rules here that are informed by the quantum resources. And maybe I'll stay for now with this example A. So let's say we have this graph, we run it on a quantum computer, and the quantum computer tells us that this node is very likely to be in the independent set. So this we found out by measuring the expectation value of some quantum operator. And since we know that this one is probably in the independent set, we say, okay, well, let's add it to the independent set. However, due to the constraints of the optimization problem, namely the independence constraint, we now know that no variable or no node that is connected to this particular node can simultaneously be in the independent set. And this then results in the simplified graph, which we would then run again on the quantum device. And this kind of proceeds in this recursive manner. For different observations or like different, let's say, correlations that one obtains from the quantum device, we devised these different rules. And I would like to emphasize that these are by no means the only rules that one can think of. And actually, this was recently also demonstrated in this paper by some folks over at NASA that kind of did a more, let's say, intense or in-depth study of these update rules. And they noticed that actually, the choice of these update rules, of course, is also very important. And there's, a lot of future research to be done on, how exactly one is, it is best to use these quantum resources. Exactly. Right. Yeah, I think one very nice feature of this approach is that since the update rules are directly motivated by the independence constraints, which is the so-called feasibility constraint, which governs whether or not a certain solution that we obtain does actually make sense in this context or not. This is directly encoded or like kind of hard coded into this procedure, meaning that every solution that one obtains by this means is actually a feasible solution. So there's no need for classical post-processing or anything like that, which I think is one very nice feature, and it also demonstrates on how to use classical updates to enforce constraints in an optimization problem.
Okay.
Any questions to this?
Yes, we have several questions. So actually, I think that at least one of them or two of them just correspond to the previous slide with yes, quantum informed recursive. There's a question about could this QIRO be considered dynamic tuning?
Dynamic tuning, I'm not familiar with that term. So what do you mean by that? Maybe
maybe
Pawel, would you mind if I comment?
Yes.
This is Vanek. So my question is that when you're dealing with robots, mechanics, you tend to have drift. They tend to get wear and they get a little bit sloppy. So could this QIRO, forgive me for not saying it properly, could you use this to dynamically optimize the movement of the robotic arms over time?
I don't see a reason why not. Having said that, I'm not sure if there's anything specific about this of this procedure that would make it particularly suitable for such a task. So I think I guess wear and tear would maybe amount to just like modifying the optimization problem slightly. However, I'm not sure if the thing that I'm proposing here would help if the solution to a slightly modified version, can you then infer something about the modified problem, incorporating wear and tear, for example. So I'm not sure. Possibly.
It might end up being too expensive, but thank you so much.
No, you're welcome.
Okay, thanks. There was also a question from Kevin, but I'm not sure if it was about this slide or maybe even the previous one. How many total trainable parameters? So Kevin, maybe you can also unmute and clarify.
Yeah, I'm trying to get an aspect for the size of the circuits that you're using. You say variational parameters here.
Exactly. So in QAOA, the parameters are actually, they come in pairs. So for each P, you get 2 parameters. So for each kind of layer, you get 2 parameters. So I think this is typically not the bottleneck in terms of, or at least at the depths that are accessible on current hardware. As for the gates, I'm not sure. I mean, of course, this is optimization problem specific. This is hardware specific. It comes down to compilation. What I can say is that for the experiment that you'll see in a bit, we only use the lowest possible depth of QAOA. So basically QAOA with P equals 1, meaning that we have 1 gamma and 1 beta, so 2 variational parameters. And the reason for that is that we can efficiently simulate this on a classical computer, meaning we don't need to have access to a quantum computer for that. So that's kind of the reason behind that. So yeah, I hope this at least partially answered your question.
Yeah, I mean, everybody's trying to keep everything minimum as far as like RAM, quantum inspired, that type of stuff. But I think where the industry is going is gaining additional understanding as far as like if we can use more quantum parameters to help improve accuracies, utilities, that type of stuff, we should, but we just don't know yet.
Yes. I mean, there, as I said, there's a trade-off, right? Increasing the depth should, in theory, lead to better results, but it also incurs greater costs on the hardware, and especially now, with all of the noise, right? The more layers of operation that one does, the more the impact of noise is also pronounced, and as such, you also lose the performance edge that would normally come from increasing, for example, the number of variational parameters or the depth of the circuit.
Awesome. Thank you.
You're welcome.
Okay, I can see that Ron has raised his hand. So Ron, you can unmute and ask your question.
Yeah, so for this slide, this is really fascinating because you actually stated that the deeper you get, the more noise you have to deal with. Have you experimented with this QAOA where, like in this diagram, you have some unspecified number of qubits they're using? So have you been able to compare the difference between adding additional variational cycles, which increases depth, as opposed to making the register size of the problem bigger?
So I'll answer these questions in two parts. First one, in terms of adding additional, like let's say making the register bigger, this is typically not done because the size of the register is given by the number of variables in the optimization problem. So this is typically held fixed. On the experimentation, so I've actually was toying around with this, and I performed some experiments on, I think, on IonQ, where I did increase the depth of the circuit, and I could see an improvement as I went from P=1 to P=2. The energy decreased. That was, I think, for like 12 qubits or something like that, just for the record. But I think then kind of the performance started getting worse and worse just because the noise started washing away all of the potential gain that I would have had from increasing P. So the hardware, I would say, is still not quite there yet for these applications.
So yeah, obviously, if you're doing like a constraint problem, you fix the number of qubits. But like in QML land, there are techniques where you're using the quantum functionality as one of the ML layers, and they're using the parameter-driven phase estimation or something. It seems to me in those cases the number of qubits seems arbitrary, or however many you have at the time. Have you done anything in those areas where you've been able to, since you've had access to QEra, now you have access to the big machine, the 256 qubit guy? I'm wondering if anybody's finding out whether increasing the circuit width is providing benefit over increasing depth.
So exactly with QEra, it's a bit difficult to say because as of now, the device is mainly operative in the analog sense. So basically, you don't have this traditional like gate-based access to it. I think this is something that the folks over at QEra are working on actively, but as of now, this is still analog. So kind of a direct comparison is a bit tricky. But actually, no. So I haven't done anything in this realm. So I'm not the best person to answer this question, I'm afraid.
Okay, thanks.
All right, I can see two more questions. Rudi, would you like to answer them now?
Yeah, of course.
Okay, there's a question from Jordan. For the iterative process, how many shots are we talking about? 50, 200, 2000?
Was that for what case was that?
Jordan, you can also unmute yourself and clarify.
Or in the paper that's published. I haven't had time to read this. I was just curious about, for the research, what was done, what were you using as the baseline for the iterative process? Was it a 200 shot? Like,
Honestly, I don't remember off the top of my head what the number of shots was, but I think it's like in the hundreds. So I think it's like I used a couple of hundred shots to estimate the correlations or the correlation matrix, and then use that. So I mean, of course, this you can vary in terms of how accurate you want this to be and so on, but this was kind of what was feasible with the resources that I had and the availability that I had.
Mm-hmm. Okay, great, thank you. And there was one more question asked on YouTube. How the Rydberg blockade helps in operating quantum gates in neutral atom quantum computers?
Yeah, so I'm not an expert in the hardware side of things, so take my answers with a grain of salt. But in how I understand this is basically you have this driver Hamiltonian which allows you to do this Pauli X-type operations, but you definitely need something which is able to couple qubits together. And in a neutral atom quantum computer, this is done using this Rydberg blockade mechanism. So this is what brings or like kind of makes the qubits quote unquote talk to each other. And I think this is why this is kind of like an essential ingredient of also gate-based computing on neutral atom devices. But that's as much as I can say to this.
Great, thank you. Okay, I think we can move on.
Yes, there's not so much to go, so don't worry. Yeah, so to summarize, quantum resources are used to obtain correlations, which then in turn are used to simplify the problem. And this we can do for a variety of problems. Here I focus on the maximum independent set problem first. There's two, let's say, natural benchmarks that we use for this. The first one being RQAOA, and the second one being greedy algorithms, which are a relatively powerful classical heuristic for MIS type problems. And there's, I think, two main findings that I want to relay to the audience here. The first one being that we observe what is actually an expected trend, but it's nice to see it confirmed nonetheless. So in the bottom of this figure, you'll see that you'll see the results for QIRO with QAOA correlations from various or from a varying quality of the parameters. So you can think of this in terms of you have quantum circuit, but you're not able to fully optimize the parameters. So naturally there's going to be some variation in how well I can optimize the variational circuit. And this will also depend on, of course, the energy and the quality of the correlations that one can obtain from such circuits. And we see here that there's a quite nice and monotonous relationship between, the better the parameters, the better also the approximation ratio that one obtains from, and this is noted, this is log scale. So, even though this doesn't seem like a very dramatic trend, it's still, I would say, substantial. And the other thing is that greedy algorithms are actually, still better, but you have to keep in mind, right? This is, greedy is for sure not the state of the art when it comes to maximum independent set, but it's a useful benchmark for now in this early stage. And the message here is that basically this is done with p = 1 QAOA, which is really the most low effort or low resources quantum routine you can use to generate correlations. And already it's not doing super badly, so it's getting something right. And actually in the paper that I showed before from the folks over at NASA, they even managed to design update rules which outperform the greedy benchmark. So even with p = 1, so there's hope that once we go beyond p = 1 QAOA, the results will improve substantially. And this gives me real fills me with real excitement to see when the hardware is here, what the actual performance will be. one very nice thing I think about our algorithm, and this is also something which separates it from our QA, is that it can be implemented to run on analog devices. So remember the instance that I showed you before with roughly 140 nodes. We borrow the same set of instances also for this particular project, and we used a QERA device, so the Aquila device with 256 qubits potentially, to generate correlations between or to estimate correlations between the variables in this optimization problem. And we again we compared this to the correlations obtained by the QAOA circuits at p = 1 and the greedy algorithm. And here I again show the approximation ratio for a collection of 10 different graphs. And you'll notice that, first of all, the greedy algorithm sometimes fails miserably, which is kind of expected from a greedy heuristic, which as soon as it makes a fatal mistake, it kind of goes into the wrong part of the solution space, and kind of is not able to escape that part. The same thing is not happening to our algorithms. The nice thing being also that there is a clear, or maybe clear is too strong a word, but there is strong indications that the correlations obtained from the QERA device perform a lot better than the correlations obtained by QAOA. And this is very nice to see, because we use a very let's say trivial benchmark in p = 1 QAOA. However, having said that, right, the numerical simulations that are performed to obtain these blue bars are without errors. There's no experimental noise, there's no shot noise, there's nothing, meaning that it's actually very, I would say, very encouraging to see results from real quantum hardware that outperform a classical simulations benchmark. So I'm also excited to see what happens once we maybe use also even more clever update steps, or when the sizes of the hardware scale to larger instances, to see if there is anything actually anything to gain with these sort of algorithms. All right, last slide on the QIRO before I conclude. Typically, what is done in quantum algorithms, I would say, even more generally than just in quantum optimization, is that improvements are obtained by making the circuits deeper. So making stacking more gates in a circuit, increasing the accuracy, decreasing the energy, whatever that may be. However, as we've discussed before, doing this in the current state of the hardware is oftentimes difficult, if not impossible. And the question that we asked ourselves was, how can we get more from the same quantum resources? And to this end, we proposed this notion of backtracking, or we kind of borrowed this notion of backtracking from the world of classical optimization. And the general idea is, in this QIRO procedure, what we do is we iteratively simplify or recursively simplify the problem. However, some of the reductions that we've made were probably not correct, right? So maybe we selected one node to be in the independent set when it actually shouldn't have been. And what we do with backtracking is we try to identify where such mistakes happened. We revisit that decision. For example, here we revisit that decision, and then we explore an alternative path in the solution tree. And you'll realize, of course, that if we were to explore all of the possible paths through the solution tree or through this search tree, this would be equivalent to just brute forcing the entire optimization problem. So this is of course infeasible. So now the question is how to choose a smart heuristic way of identifying these mistakes. And we proposed something in our paper, which was a very simple kind of depth one backtracking, and we implemented it for the next two set problem, which is another very famous optimization problem. And we plot here the results again, RQAOA, QIRO, and then QIRO with this additional backtracking. And we compare it to simulated annealing, which is another, I would say, well-established classical benchmark. And you'll see that, first of all, for a certain regime of instances, actually we're able to outperform simulated annealing. Of course, simulated annealing is also heuristic, which you can improve and invest more resources in. But for, let's say, reasonable resources, we were actually able to outperform it, or at least perform comparably with it. However, this kind of changes as we increase the density of the problem. And the second thing is that basically you also notice that QIRO performs much better than RQAOA. The reason for this is that here we actually use some tools from satisfiability solvers. So basically, the kind of the study of such problems, also called satisfiability problems, yielded a plethora of techniques which are able to effectively simplify these problems. And by just leveraging these in the course of our QIRO optimization routine, we were able to gain some ground on our QAOA. I would say that like investigating such backtracking strategies is likewise a very interesting field of future research, and we're excited to see what the community is able to do with our proposal, and if there's any interest in that going forward. All right, it's been almost an hour, I think, or even more so. So I would just like to take this opportunity to again flash the results, or two key graphics from the works I was presenting, and take a moment to acknowledge my wonderful collaborators, Martin Schütz, Helmut Katzgraber, and Kyle Brubacher from Amazon, Professor Nishimori from Tokyo, Christian Mendel from TOM, and Aaron Kerschbaumer, who's now at IST Austria. And yeah, thank you for your attention. And yeah, maybe just one last thing. I can use this as sort of an advertising platform for our quantum computing application benchmarking tool called Quark, where the community is invited to take their quantum computing applications and then test them against various classical benchmarks, but also try different quantum algorithms on them on different quantum hardware, and let's say compare the performance of the different algorithms. And we kind of came up with a open source Python framework to do this, which you'll find on this link. So if there's anyone here that's working maybe in an industry or university setting where such a framework would be of use, you're more than welcome to use it. And of course, also feel free to contribute to this Quark community. With that, I would like to thank you again for your attention, and I'm happy to take any remaining questions that you might have.
Great. Thank you, Rudi. Thanks for this great presentation. And yeah, it's time for Q&A. Let's see if we have more questions now. I can see one question from Ron. So, what was the largest MIS graph in terms of the number of vertices that you were able to solve with the neutral atoms using the Rydberg phenomena? And Ron has probably found the answer. It looks like it's around 140, but maybe you can confirm.
Yes,
which is great.
Good. Good. Good listening skills.
All right, great. Do we have more questions? I don't see more questions on our chat now. Maybe Ron would like to ask a question. Please go on.
So just fair warning, I went through the QAero boot camp as part of the Womanium Global Summer School a few months ago, and for me it was one of the most impressive things that I learned in terms of running quantum algorithms and producing real world results on problems that are useful, like the MIS problem. So when I heard that QAir's 256 qubit machine became available, I got really excited. But then I heard people start squawking about how much it costs through Amazon. Are you aware what the cost is, or are you insulated from that? Anything you can say about that?
Yeah, so what I can say, I don't have the numbers. I don't have the numbers in my head, but of course, it helps to have, some industry backing in this. But I have to say that I was actually on the opposite side of, I didn't, compared to some of the workloads that I'd run previously on some of the other providers, I would say that that the price did not differ substantially from other vendors on Amazon. So I would say it's not if it's an issue, it's not an issue of, I would say, QAira specifically. I think it's probably then of the entire ecosystem.
Yeah. Okay. So and then also, did you experience long queue delays? Did you get the feeling that they had more than one machine available, or do you think they just have one machine available currently?
As far as I know, I think it's just the one machine. Because also at the beginning, the availability was limited to 10 hours a week. Because I guess the rest was, like dedicated to either their own experiments, but also to maintaining the device. Right? If you only have one, lab setup, I guess this requires some maintenance, right?
It'll become real exciting to see them ramp up and maybe get more machines online and get the costs down, so that it's not just big corporations taking advantage of it. But,
no, definitely.
Thank you.
Okay, great. There's one more question on our chat. May you please elaborate the meaning of HP and the related formula? I think it's related to one of the previous slides.
Yes. Yeah, I completely keep that in the interest of time. Basically, there's been some research done actually from the people over at Harvard that one can classify the MIS problems in terms of their difficulty, so to say, or their algorithmic hardness. And one can actually capture this to a certain extent using this hardness parameter HP. And this hardness parameter is actually computed in a very simple way. So I can explain the terms in this equation. So this MIS minus 1 is just the number of the different configurations that are nearly optimal. So you can imagine, you have some optimal configurations, with the optimal number of atoms that are colored purple in this case. But you also have, some configurations which have like one atom less color. And this is the number of, such configurations. In the denominator, you see the number of, the optimal configuration. This is just the size of the independent set. And the intuition behind this is basically that sort of like it's difficult to get from, nearly optimal solutions to the optimal solutions. And that kind of this ratio between the number of such nearly optimal and optimal solutions is what determines the hardness for a family of classical algorithms.
Okay, great. Thanks for the explanation. Kevin has raised his hand. So Kevin.
Yeah, I had a question. So of all these projects, which is closest to market?
Yeah, I'm, as a PhD student, I'm probably the wrong person to ask, but I would say I'm excited where the QAira technology is going, as it was also mentioned in the previous question. And even though the sizes that we're seeing now are still in the couple of hundred nodes, which I think are easy to be solved with classical algorithms, I would imagine like once we hit thousands, maybe tens of thousands, that this is no longer the case. And I mean, it will be interesting to see how the quantum technology scales in terms of how difficult it is then to design algorithms for such things. But I mean, if I would say this is probably in the realm of quantum optimization, the neutral atom quantum hardware is definitely the one that I'm most excited about.
Okay. Now for the annealers, were they both the same qubit count for the simulated and I'm assuming the other one's D-Wave?
I didn't use D-Wave at all. So no, the simulated annealing is actually the thing that I mentioned there. So this is simulated annealing, not quantum annealing. Maybe I was a bit unclear with that. So simulated annealing is a purely classical algorithm, which has been used for, I would say, 4 decades now. That has nothing to do with quantum computing or quantum annealing. Even though quantum annealing, I would say, probably partially borrowed its name from simulated annealing. So that's kind of the
okay. So
story.
you didn't use a simulated quantum annealer.
No. This is a simulated annealing classical algorithm used as a benchmark.
Okay, thank you.
Okay, great. Thanks, Kevin. Do we have more questions? Rudy, there is another question. What are applications of the current solutions of MIS and max to SAT problems in industry today?
Yeah, sure, I can comment on that. So for the maximum independent set problem, I know of several applications. One very, let's say, straightforward one that I can, I think, explain quickly here is, let's maybe go here, would be, for example, placing antennas. So let's say you're a telecommunications company and you have a map and you're trying to place antennas on the map. But at the same time, you don't want to put antennas too closely, because if you put 2 antennas, too close to each other, the signals might interfere. So you're trying to find these, independent spots where you can position antennas. And, like if you can save on a couple of antennas, maybe that's, saves you a couple $1 million when you, do this for the whole of the US, for example, right? So it's a, one, I would say, very easy to see application of such problems. For satisfiability, so max to sat, I think, in general is like I would say, quite cherry-picked problem, in the sense that, we used it because it was easy to map, and, we're still in, I'm working in academia at the moment, partially at least. So I have the freedom of doing that. But in general, I would say satisfiability problems are, for example, used, I think, in software testing. I also know of a use case within BMW that was concerning, let's say, producing test vehicles, and then you had like certain rules on test vehicles that you could model as satisfiability formulas, and then you were trying to find assignments which that kind of don't violate clauses, which would kind of mean that's an infeasible car to build or stuff like that. So there's while maybe not directly these problems, but kind of the broad family of problems is for sure interesting also for industry.
Okay, great. Do we have more questions?
Okay, I'll have one more.
Yes.
So one of the extra dimensions of the neutral atoms is under your program control. As part of your algorithm, you can physically position the neutral atoms within the space. I know you had some graphs that kind of showed that. Were there any specific things you ran into where you really took advantage of that? And again, one of the problems I saw was they actually took the atoms and mapped them to a physical map of Boston. And so each atom represented something in Boston, and then they were running these MIS programs. But did you have anything like that you were experimenting with?
Yeah, so for example, like the example that I gave before, right, the map of the US and the antennas, right, this is something that could be done in a similar way, where every atom on the map of the US would correspond to a potential antenna placement. Yeah, I mean, it depends, right? To some extent, yes, and every of this graph kind of inherently uses this fact that you can position atoms kind of by design, but in the sense that I didn't do any fancy maps of Munich, for example, or Germany, and use that. But it's a good idea maybe for future, for some nice figures for my PhD dissertation, for example. I might take advantage of that as well.
Sounds like a lot of fun. Thanks.
Okay. Thanks for asking, Ron.
Sorry,
Thanks
Pawel,
for
can I ask a question?
Yeah, sure.
I did ask on the chat. My experience, from classical optimization, sometimes we spend a lot of time in setting up the model and then debugging it, and we're under pressure to deliver the results within certain timescales. So I wonder, what are the benefits of the quantum optimization over classical? And also, if you could comment on the times of setting the models.
Yes. Yeah, two things. First of all, on the benefits of quantum optimization versus classical, I think that's the million-dollar question. I don't know of anyone that has, a very clear answer. I think it's kind of sure that I think quantum computing can give you this quadratic speedup, kind of like a Grover-like speedup for the solutions. However, and I think this kind of is like a nice segue to the second part of the question, this has been oftentimes shown to not be sufficient to really, yield, I would say, practically relevant speedups. Because, as you imagine, because also, one problem is, that quantum computers maybe are sometimes just slower than in the very advanced classical components that we have at the moment, in terms of, the actual clock speeds. So arguably, you lose the overhead of a quantum computer is then kind of too big to effectively harness the quadratic speedup. As for the modeling, I think in this case, I agree. Like modeling, I think is, as I've come to realize also during my stay at BMW, is that this is oftentimes the most useful part, you do as an optimization specialist. But I think it's, well, for sure, right? If you want to use the quantum computer by any means, yes. I mean, sometimes it might be more tricky, but for these, like, let's say, tailored applications, like the ones that I showed, I think there's probably not a big difference between like mapping something to a classical computer or to a quantum computer, provided that the mapping on the quantum computer is actually, like feasible, like, for example, in the sense of, in the case of antenna placement.
All right. There's one more question from Jordan. Is backtracking the equivalent as backpropagation in classical machine learning in the way you are using it? Mm-hmm.
No. So backpropagation in classical machine learning, if I'm not mistaken, is a way to kind of propagate the gradient information in a neural
Mm-hmm.
network, kind of through the network going back from the output layer. In this case, backtracking is sort of like, I don't know, like you imagine you walk through a maze and then you get lost and then you try to think, oh wait, where did I make my mistake, and try to go back and take a right turn where before you took a left turn and hope that maybe now you're going to get out of the maze. I think that's, I would say, the most high level overview I can give of this procedure.
Thank you.
Okay. All right.
You're welcome.
Thanks. Okay, so there are some acknowledgements on the chat. So we also thank all participants. Do we have more questions? Maybe last chance to ask. There are questions about the recording. So you can find the recording on the YouTube channel of Orion X. Maybe Helen can also clarify and provide the link. I believe there will be a link shared on the website of this meetup at meetup.com. Oh, thanks, Helen, for sharing. There's a question also about the slides. Jernej, would you also like to share the slides? So usually Helen just distributes the slides.
I'm already in touch with Helen. I'll provide her the slides after the talk.
Okay.
I'm happy to share them.
Great, thanks. All right. Any more questions? Yeah, Helen is the best. I think we can agree. That's a good comment. All right. So I think we can conclude. So Jernej, thank you once again for, first of all, for the great presentation, accepting our invitation to give this talk. There's maybe also just a general question now from Philip: where would a beginner go to learn fundamentals about quantum computing? Maybe I can also share some links here on the chat, or maybe I'll share the links to Helen, and Helen can send them to Philip. So Jernej, thanks for giving this talk and for answering all the questions. This was very good meetup. I believe that we've learned a lot, and all the comments in our chat can confirm it. So we also thank all the participants for attending, and we hope to see you next time on our next meetups.
Thanks for the invite, and thanks for staying patient throughout this talk. Yeah, have a nice rest of the Saturday.
Yes, you too. Thank you.
Bye bye.
Have a good weekend, everyone. Thanks. Bye bye.